From raw materials to finished products, the textile industry uses steam as a heat exchange medium. Steam heats rotary cylinders, air coils, shell and tube heat exchangers, jacketed kettles, and absorption chillers. The condition of any component in the steam system can seriously affect the efficiency of the entire operation. Operating steam equipment at peak efficiency can lead to increased production, improved quality, and lower production costs. Rotary cylinders. Foremost among the heat transfer equipment used in the textile industry are rotating steam-heated cylinders, such as dry cans, slashers, draw frame rolls, and sanforizers. Dry cans are typically used to dry cloth or heat set a non-woven web after the moisture has been evaporated. The rotary cylinders of the slasher dry a starch coating called size, which is applied to yarn in preparation for weaving. Synthetic fibers are heated and stretched on draw frame rolls. The sanforizer pre-shrinks fabric by wetting the material and then running it over one or two dryer cylinders. For many years, the textile industry has used the Armstrong inverted bucket trap in conjunction with a stationary siphon pipe to drain rotary cylinders. The inverted bucket has an intermittent discharge that purges air and condensate from the cylinder, while air is continuously vented through the bucket vent. The simple yet extremely rugged construction of this trap allows it to provide a long, trouble-free service life. Since large volumes of air are often present in these rotary cylinders, particularly on startup, it is recommended that the inverted bucket's air handling capabilities be supplemented by an external thermostatic air vent. In response to the demand for ever-increasing production rates and considering the spiraling cost of energy, a new steam and condensate drainage system has been specifically designed for the steam-heated rotary cylinders found in the textile industry. The Armstrong-Johnson Heat-Tech system has proven effective. The major components of the Heat-Tech system are rotary siphons, rotary joints, differential controllers, air eliminators. Condensate, air, and a small percentage of blow-through steam enter the siphon pickup. This biphased mixture flows through the siphon out of the rotary joint to the differential controller. After this mixture enters the differential controller, the vapors, air and steam, are separated from the condensate. The condensate is discharged through the orifice into the condensate return line. The vapors flow into the secondary steam header, held at pressures slightly lower than supply steam pressure. Then, the thermostatic air vent removes all the non-condensable gases from the steam. The secondary steam from a number of differential controllers is condensed in a cylinder that is maintained at a slightly lower pressure than the remainder of the cylinders. A rotary siphon, as the name implies, rotates with the cylinder. This siphon has a fixed tip-to-shell clearance, as opposed to the stationary siphons which dangle from the journal. As a result of the design, rotary siphons are not susceptible to breakage, which is a frequent problem with stationary siphons. On siphon drainage systems, a conventional trap may close prematurely on a false signal caused by flash steam and air. This does not happen with the differential controller, since these vapors are removed from under the inverted bucket. The condensate discharge mechanism continues to function, closing for live steam and opening for condensate. The surging action caused by the intermittent condensate discharge pumps non-condensables and condensate out of the cylinders. The differential controller will automatically adjust the pressure differential across each dryer in response to the load. The air eliminator senses the temperature depression caused by the presence of non-condensable gases such as air. It automatically opens a valve to discharge the air from the system. When the air has been removed, the valve automatically closes, avoiding the loss of steam. The HeatTech system will provide these advantages over the conventional trap stationary siphon system: air elimination at each stack, quick startups, increased thermal efficiency, uniform temperature profile, immediate temperature response, lower production costs, higher production speeds. In conventional systems, air is returned to the boiler along with the condensate. With the HeatTech system, it is removed at the cylinders, minimizing corrosion and deaeration problems. Tests have proven that the HeatTech system is capable of reaching operating temperature in 10 minutes, as opposed to the 1 to 3 hours required with a conventional system. Higher heat transfer efficiency is made possible by carrying lower levels of condensate and air in the cylinders. In tests conducted on the same machine under identical operating conditions, cylinders drained with the HeatTech system had an average surface temperature 20 degrees Fahrenheit higher than a trap and stationary siphon system. During the same tests, the cylinders drained with the HeatTech system had a much more uniform temperature profile. This resulted in greater uniformity in drying and higher quality product. With air and condensate, which act as barriers to heat transfer, held at very low levels, the cylinder can quickly respond to changes in steam supply pressure. Maintenance costs are reduced, since there will no longer be broken siphons to replace. With lower condensate levels in the cylinders, they can be driven with a reduction in brake horsepower. The HeatTech system is designed to operate effectively and efficiently at speeds in excess of 1,000 feet per minute. On installations where the HeatTech system has replaced conventional drainage systems, up to 25% production increases have been realized. Some steam-heated rotary cylinders found in the textile industry are not conducive to the HeatTech system approach. Slashers, for example, may be grouped with a single control valve for several cylinders. Many of the benefits of the HeatTech system can be obtained by using rotary siphons and differential controllers with the bypass steam piped to the condensate return line. Air coils. Steam is used to heat air in many different applications in the textile industry. It may be used to control ambient temperature within the plant, or it may be used to heat air, which is in turn used to dry products. In either case, a properly designed steam and condensate drainage system must handle the condensate and air at all times, allowing the air coil to operate more efficiently, preventing the damaging effects of corrosion and water hammer, and eliminating the possibility of freeze-ups when the coil is heating low temperature outside make-up air. Preheat and reheat coils used within a ventilation system and unit heaters are examples of the equipment used to heat the plant. Although these air heating coils come in a variety of shapes, sizes, and construction, the steam and condensate systems have certain things in common. These air coils are typically supplied with low-pressure steam or have control systems which may modulate to very low pressure. An F&T trap with an integral vacuum breaker will perform very well under these service conditions. Grid-type coils have a tendency to allow the formation of air pockets, resulting in non-uniform temperatures across the coil. The installation of a thermostatic air vent at the high point of the discharge manifold eliminates this possibility. At times when the heating load to the coil is reduced, the steam control valve will modulate, causing a reduction in steam pressure to the coil. The steam pressure may be reduced to a point where the collapsing steam in the coils generates a vacuum at the trap. When this happens, the integral vacuum breaker in the F&T will open, breaking the vacuum by admitting air. With the vacuum broken, gravity will cause condensate to flow if a drip leg of sufficient height has been provided. This, of course, will prevent flooding of the coils. Elevating condensate should always be avoided. However, if it is absolutely necessary, a safety drain and a check valve should be provided. The safety drain will discharge the condensate load only when the pressure is insufficient to lift the condensate to the return line, while the check valve will prevent the backflow of condensate into the coils. When the load on the air coil is again increased, the steam pressure will rise. At this time, the thermostatic air vent in the F&T will vent the air which has been introduced through the vacuum breaker, allowing the coil to quickly respond to the increasing load up to its maximum output. If the steam pressure is held constant, or a higher pressure of steam supply is used which is not likely to modulate to the very low pressures, the inverted bucket trap would be recommended. Under these conditions, the inverted bucket has certain advantages over the F&T type trap. It is more resistant to hydraulic shock, is more capable of handling dirt, and generally gives a longer service life. Steam-heated air coils used on production equipment typically fall into this category since they operate at higher pressures. These air coils are normally incorporated in tunnel dryers, such as the tenter frame oven, the tow dryer, or the loop dryer. The coils in these pieces of equipment heat the air, which in turn heats and dries the fabric by evaporating moisture from it, or, in the case of the tow dryer, the heated air may be thermally setting synthetic fibers. These dryers are often used in lieu of dry cans. The loop dryer, for example, is used to dry fabrics such as terry cloth, which, if dried on dry cans, would result in the matting down or sticking of the nap or pile. Air coils, like all steam-heated pieces of heat transfer equipment, should be individually trapped. If two coils are group-trapped and the first coil has a higher load, a greater pressure drop across the first coil will exist. This results in partial flooding of the first coil. Again, if the coil is of the grid type of construction, a thermostatic air vent should be installed at the high point of the discharge manifold. On any of these types of coils, the operating characteristics of the inverted bucket trap can be very beneficial. The intermittent discharge causes momentary pressure surges, which continuously purges air and condensate from the coils. This condensate drainage system will make a high heat transfer efficiency possible, which, of course, can lead to higher production. Shell and tube heat exchangers. Shell and tube heat exchangers are another piece of steam heat transfer equipment widely used in the textile industry. They perform a variety of functions, including the heating of water or dye. For example, dye may be pumped through a shell and tube heat exchanger, where it is heated before being circulated through a keyer, containing spools of yarn to be dyed prior to weaving. These heat exchangers frequently are supplied with low-pressure steam or have control systems which modulate to very low pressures, as is normally the case with storage water heaters. This creates drainage problems similar to those that we discussed in relation to air coils, having the same steam supply conditions. Since the F&T trap is particularly suited to the handling of large volumes of air and condensate at low pressures, it is again recommended. A vacuum breaker and drip leg of sufficient height are essential to prevent the flooding of the heating tubes that can occur when the control valve modulates to extremely low pressure. It is essential that the horizontal heating tubes be kept drained of condensate at all times to avoid the damaging effects of water hammer and corrosion. Thus, a safety drain and check valve are highly recommended. The safety drain will discharge the condensate load when there is insufficient pressure available to overcome the back pressure in the condensate return line. The check valve will prevent the backflow of condensate into the tubes. If the steam pressure is held constant, or a higher pressure of steam supply is used that is not likely to modulate to low pressures, the inverted bucket trap with a large vent is recommended. Air pockets are likely to form in shell and tube heat exchangers with steam in the shell. In order to prevent this, a thermostatic air vent should be installed at the high point of the shell. Keeping these heat exchangers drained of condensate and air at all times will ensure maximum performance. Jacketed kettles. Another use of steam in the textile industry is in the preparation of size. Size kettles, or starch cookers as they are sometimes called, are used to mix and cook the starch. After the size has been prepared, it may be pumped into another stationary jacketed kettle where it is stored until needed. If the size kettle has a direct steam injection coil, a drip trap ahead of the control valve should be used to protect the valve and coil from the cutting and eroding effects of wet steam. Frequently, size and storage kettles are built with a steam jacket. A thermostatic air vent should be installed at the high point of this steam chamber. With an inverted bucket trap having a large bucket vent on the condensate outlets, there is a very effective drainage system for any kettle. The thermostatic air vent rapidly vents the air in the steam jacket on startup. The inverted bucket purges condensate from the jacket. Removing air and condensate brings the kettle quickly up to temperature, resulting in the maximum production potential. The inverted bucket trap provides a long, trouble-free service life without steam loss. Some of these kettles, particularly the storage type, are equipped with submerged coils. Here again, the inverted bucket LV will provide excellent performance. If the physical size of the inverted bucket trap is a problem because of serious space limitations, the balanced pressure thermostatic bellows trap is an acceptable alternative. Steam absorption machine. Temperature and humidity control is important throughout many of the processes in the textile industry. A controlled environment helps to control dust, remove static electricity from the product, and provide a more healthful atmosphere for employees. Steam absorption chillers are often used to provide the tremendous quantities of cool air required in textile mills. The F&T trap with an integral vacuum breaker is ideally suited for draining absorption chillers. It provides an even, modulated flow and will save energy since it doesn't waste steam. During the operation of the chiller, the cooling load may be reduced, causing the steam control valve to modulate. Steam pressure to the concentrator section of the chiller decreases, possibly to the point where collapsing steam in the coils produces a vacuum at the trap. Then, the vacuum breaker will open, breaking the vacuum by admitting air. With the vacuum broken, condensate will flow if a drip leg of sufficient height has been provided. Keeping the concentrator free of condensate allows the system to retain its controllability and prevents freeze-ups. In addition, avoiding partial flooding of the coils eliminates the possibility of damage from water hammer or corrosion. As the cooling load on the chiller increases, the steam pressure rises. Then, the thermostatic air vent in the F&T will vent the air which entered the steam space through the vacuum breaker. Thus, the chiller quickly responds to the increased cooling load. An inverted bucket trap with an external thermostatic air vent would also be acceptable for draining the steam absorption chiller. Regardless of the trap used, a standby trapping system is recommended for this service. Should a component in the drainage system need maintenance, the chiller can operate on the standby system while the repairs are being made. The standby trap ensures continuous, uninterrupted service. Throughout the various processes for manufacturing textiles, steam is used as a heating medium. Keeping your steam system operating efficiently can increase production, reduce operating costs, and improve the quality of your products. Your Armstrong representative can give you more information on the benefits of using Armstrong drainage systems on your equipment.